Okay, so okay, it says that's better. So thank you. Okay, so computing longest increasing subsequence. So the classic algorithm is to use patient sorting. Algorithm takes like 70s. Will run in time, which is n log n. Okay. So now the question that we are asking here is, how can we do that? Can we do faster? In particular, the question is, can we do much smaller than time n? Okay. So that would put us in the regime of sublinear time. Okay. So this is a problem that has been studied before, and basically the first question to be solved is studied in the context of property testing, monotonicity testing in particular, which is basically a function which is one-dimensional. Monotonicity testing in this case corresponds to checking whether the sequence is fully sorted. So the LIS is n versus a little bit less by a factor of 1 minus epsilon. Okay, so this has been studied in a sequence of papers, in particular PCCL paper. It was done here by Bernard Chazelle and this is the time students here, and yeah, so lots of work has been done here. So what can we do? In other regimes, not n times 1 minus epsilon. What if LIS is much smaller than around? Okay, so the next the paper in the sequence was to get additive approximation. So computing this length up to additive epsilon n approximation, and this can be done in time which is basically dependence on n is quadratic, but dependence on epsilon is exponential. Okay, so this is good if your epsilon is basically a small constant, but not much less than, let's say, something like 1 over log n. Okay. So much more recently, the focus has been on how on getting handling the other regimes, and in particular, you should think about the context where the LIS, let's say, is of weight or length, which is n divided by k for some parameter k. Okay, so the recent results have shown that you can get basically k approximation in runtime, which is root n times k squared. So let me explain what does it mean to be k approximation. So this is this is for k cubed approximation, which is the first paper. Here, the second one achieved k approximation. But it needs to distinguish, let's say, LIS, which is bigger than n divided by k versus n divided by k cubed. It doesn't mean k cubed approximation. So, the approximation would be n by k versus n by k squared. Okay, so this is this is one result. Another result obtain a better approximation just equal to epsilon, but runtime really kind of gets very, very close to linear. So the runtime is n 1/4 of epsilon as well. And just to put it in context, what should we expect from this problem? Okay, you should compare this to kind of simpler version of the problem. That feels kind of a related problem. We are given a sequence of 0 ones, estimate the Hamming weight of the vector. Okay, and suppose your Hamming weight of the vector is something around n by k. Okay, so just standard sampling and estimating the weight would give you 1% from approximation to the weight of this vector in time which is about order k. Okay, so you can notice immediately that k time is needed to even find a single one, random sampling just to find a single one in this vector in order to time k. So just a little bit more, you can estimate this weight quite well. Well, the question is, can we do something similar for LIS? Okay, it is not clear why LIS should be much, much farther than this. Okay, so basically the main question here is, what is the complexity of estimating LIS? Can it be similar parameters as estimating the Hamming weight of a sparse vector? In particular, the previous result would not be sublinear time when LIS is of length which is less than n to 3/4. Okay, so there's no gaining over patient sorting in this regime. And you should think about what is kind of natural value of LIS. But if you look at a random sequence, then LIS is already of length for 10. So this means that this algorithm shouldn't be able to tell a random permutation versus a random permutation when you have something planted there, which is a little bit off. Okay, so our result is basically looking at this problem, and we give an algorithm that computes an approximation which is subpolynomial, so k to the to of 1, with runtime, which is basically k times a factor, which is again subpolynomial n, so n. For example, in this regime of subsequence LIS being about root n, this means that we can distinguish LIS of like root n versus root n time n to half plus equal of 1 in time about root n. Okay, so this is at least kind of as improvement of our previous results, super improvement, because previous results had both polynomial approximation and polynomial slowdown runtime. This is a sublinear time algorithm. It samples the sequence to give, basically give this length of LIS. It's non-adaptive sampling. Okay, so it does not. It just issues basically a list of positions to sample. It samples them, and that's it. It doesn't access the same after that anymore. The runtime again is optimal fun because runtime is needed even to to sample and kind of even hit a single element from the LIS. And kind of as a post-realization, it turns out that there is a black box reduction from sublinear time for LIS problem to computing longest common subsequence in linear event time. Okay, so in particular, the computing or estimating the longest common subsequence between two strings in linear event time has been studied recently. Only recently, there has been some non-trivial approximations. The type of approximations that has been known until recently is n to 2.5, so some polynomial approximation in linear time using. So this was basically an observation that I just made. That one can basically reduce black box longest common subsequence to sublinear LIS, and whatever approximation you get there for k equals to n, you get the same for those things. Okay, so this means that we can estimate longest common subsequence in linear time up to approximation, which is subpolynomial. Okay, and the reduction, I have a backup slide. I can see it toward that. But it's very kind of relatively standard actually. Reduction, at least the construction that you can, given x and y, you can build some implicit string z, whose length will be at most n squared, somewhere between n and n squared. The construction is something common for all such problems. And the main observation here is that for the construction, the longest common subsequence in between x and y will be exactly the same as the LIS of this implicit string z, and the LIS of this implicit string z is guaranteed to be at least a fraction of 1 over n of the entire length of this string z. So we can basically run this sublinear time algorithm LIS on this implicit string z. Implicit, I mean that for any position you can, let's say, polylog time, polylog n time, output what is the character of this position. Okay, so you run just the algorithm and you get subpolynomial approximation. Okay, so time for me to stop. See if there are any questions. If not, then basically I'll start talking about how we do.
Yes.
Well, this is not as, basically this is not a sublinear time regime algorithm. You can sorry. No, it's quadratic time. Longest common subsequence is basically the same as any distance. It's just they complement it, right? Computing longest common subsequence is probably I should say more a little bit about it. This is kind of a classic linear programming that solves in quadratic time. And it is under the strong exponential time hypothesis, we cannot solve it faster than basically quadratic time. Okay, there's no hardness. I'll mention this later. There is no similar kind of hardness approximation in the singular set or any other kind of plausible conjecture. So we don't know really, what should we expect to get in linear. Now this is not a sublinear time regime, so this means that even if we output answer, even if your LCS is, let's say, of length 10, just a constant, in which case linear length time is necessary. Any other questions? Okay, so let's do it. So I'll start with kind of a technical setup, and this is some of the setup is borrowed from previous papers. So this is the general kind of approach. So I guess as many problems on sequences, the first step you do, you take the sequence, split it up into a bunch of blocks. Okay, so we'll divide the sequence into p blocks. We'll call them x1 through xt. Okay, of length n divided by d. There's an example. And you should think about this number of blocks as being integers. They were, probably also a little bit surprising. Okay, so then eventually it is a recursive algorithm. Okay, so what we do is the following: for each block, we sample a bunch of values, right? So this is random positions. We sample a bunch of values. For each block, we sample k values. Okay, about k values, which means that in each block, you're likely to hit a few elements from the real element. So, all right, so we sample k values, right? So this means that this will be called sets S1, S2, basically sets for each block. Okay, so what we expect after this is that each of these sets will have, let's say S1, will have a few elements which are from our real longest. Okay? So for every such sample set, S1, okay, we'll consider all possibilities of endpoints, right? So here, for example, we'll call these y's, right? So y, the first index corresponds to S1, this corresponds to block 1. And the second index is, just counting these different candidate intervals. So these are what we call candidate intervals. So basically, you think about this taking all pairs here, which means that one of these candidate intervals will have both kind of low point and end point from the real LIS. Just because we expect that there are a few LIS elements in this set, and that should capture kind of a good fraction of the LIS from that particular. You just don't know which one of them, but at least one of these candidate intervals should basically bound from the below and from above the portion of the real LIS defined in that particular. Okay. Being a little bit careful, taking these intervals as being dyadic, we can generate only k such candidate intervals per every block. Okay, but it's still relatively large, which will come in. It's important later on. Okay, so this is what we do. Okay, and why we do this, will be clear pretty soon, that we will somehow rephrase the problem as certain kind of recursion. So for each such candidate interval Yij, right, we can define Lij as being the LIS from this block, whose values are only in that range. Right? So for example, for this Y11, this means that L11 will correspond to the LIS in this block, where values are only allowed to be in this range. Okay, so this is kind of putting upper and lower bound on the values of the LIS in that particular block. We'll call that Lij. Okay. So here is kind of important fact where why what we get candidate intervals is that not too hard to prove, but basically we can decompose the LIS of the entire sequence, okay, as basically, let me try to find this formula, right? So we consider all possible monotone functions gamma. Okay? Monotone function gamma is basically a selection of these candidate intervals which are strictly on top of each other in terms of value. Okay, so we maximize over all such selection of candidate intervals for each block, and we sum the length of the increasing sequence for corresponding block in the corresponding range. Okay, so here is an example of a choice, this little gamma, basically chooses a candidate interval from each block such that they are strictly on top of each other. Right, so this means that if we take an LIS with values restricted here, plus an LIS with values restricted here, plus an LIS restricted here, these are in some sense independent problems, and we can just sum up. We get some increasing sequence by taking the maximum increasing sequence restricted to this interval. This interval. Okay, so yes.
Why is it not exact?
Why it is not exactly equal to this? Because these candidate intervals are not exactly captured because there are samples, but yes, roughly. I mean, it is a constant. And you can push this, at least, taking sufficient number of these candidate intervals, you can actually make it, let's say, 1% for approximation. Yes. Yeah. Okay. So the new goal will be to estimate this value, right? So maximum over all basically monotone functions over the blocks, okay, of the sum of the best LIS inside each block when restricted to the corresponding candidate. Okay. So you can think about this as the problem is being decomposed into essentially two things, right? One is the, optimizing over gammas. Right? This is basically the global LIS. Right? This is the, taking this, this block, that block, and the local LIS. Local LIS is saying, once I restrict here, I will find the best LIS when my values are restricted. In this interval. Right? So this is, basically at the end of the day, and we'll be doing recursion for both these problems. But so far, so good. Okay, so here is how we solve basically this decomposed problem. Okay, so first of all, let me introduce a different problem. I mean, it's a different model, really. It's the same problem, but under slightly different model. You'll see how it connects to our problem after that. This problem is called Genuine-LIS. Okay, so here is how it is, right? We're still looking for longest increasing sequence. Okay, but the model is the following. We have a sequence. Okay, we have free access to the entire sequence. Okay, but some elements are genuine and some elements are not genuine. Okay, what it means is the following: that when we want to find the LIS among the genuine elements, okay, and we can look at the elements, right? But somehow, we think about them as being characters, for example, right? We have to pay for testing whether a character is genuine or not. Okay. So again, the goal is, the orange colors are the corrupted or non-genuine elements. We need to find the LIS among the genuine elements. Okay, so the longest subsequence, and our cost is how many times do we test whether a particular element is genuine. Okay, is the model clear? Yeah, so I mean, it's to the best of our knowledge, it's kind of I haven't seen this model before elsewhere. It was like an interesting new model. So we'll, in some sense, connect this to LIS and we'll see how to solve this genuine LIS. Okay. Just a quick remark, somehow, to connect it back to the superior phenomenon. You can reduce the genuine LIS to the sublinear LIS form. Okay. Mainly whatever we can get, in terms of the number of, the runtime samples for sublinear LIS problem, the approximation guarantee, we can get the same for genuine LIS, where now it's not the samples, but tests for genuineness or not. And the reduction is as follows. So we're trying to solve the genuine LIS using the sublinear algorithm. So basically, sublinear algorithm just goes there and samples positions, right? And each LIS sample that looks at a character actually generates a genuine test. Basically, tests whether that particular character is genuine or not. If it happens to be not genuine, so if I cannot possibly use this character, that's a bottom that not to be used. No, we have no assumption on the structure. But sure, the length of the LIS cannot be large. The number of genuine elements is really small, less than n by p, for example. But there cannot be an LIS of length that is n by p. But if the fraction of genuine elements is bigger than n by p, then I can, after p samples, I'll see some genuine elements. But yes, you're right, that the fraction of how many genuine elements are there will be important, and we lead basically to two approaches for solving this problem.
So you just
Yes, yeah. The length of the LIS is a lower bound of the number. Okay, so this is a model. Clear so far? All right, so let's see how it connects to our approach to the LIS problem. Okay, so remember, for the LIS problem, we need to estimate this quantity, right? The maximum over all basically global alignments of summation of the local alignments. Okay. So first of all, remember that we have, this maximum is all that, possible candidate intervals. Right? So this is taking these candidate intervals, which are strictly increasing. Okay, these YIJs are in some sense free for us, right? Because we generated them by sampling those kind of sets and then generate candidate intervals. So YIJ are something that we built. You can think about this as we have full access to these quantities, but computing LIJ is expensive. This is a recursive call, right? It says, well, we have a block of length almost linear in length, just a little bit less, and we want to compute LIS of length, something. Sorry, with values restricted to some range, and it's potentially expensive. It requires. Okay, so let's reduce formally this problem, approximation problem, to the Genuine-LIS problem. So first of all, we can do kind of the following, relatively standard discretization that, let's say, this is taking the summation of the LISs, the summation of the LISs over all blocks I. Basically, let's say logarithmic approximation, is worse than that. Is maximum over all the scales, powers of 2 of the summation of the indicator variable, wherever this LIS is at least of length. And then if LIS is at least of length t, then we say diffusion. This gives, let's say, which means that putting this observation, that the summation is basically maximum over all the scale for this, putting together this maximum, we have maximum of maximum. We can switch the maximum around. So this will be the same as the LIS is now the same as up to some logarithmic approximation is maximum over all the scales. So the maximum over all these monotone global functions of the summation of these indicator variables times t. And now you can observe that if we parenthesize it this way, this is maximum over all the monotone functions, this global monotone functions, so the summation of the indicator variables, whether LIS is sufficiently long. This is our genuine LIS problem. Okay, this genuine LIS problem corresponds to the global LIS. Okay. Right, so the genuineness flag are basically a block I that once we a block ij is genuine, if its length, the LIS length is at least t. It's the maximum overall t, just we fix a concrete t. This is this character. So you think about this gamma ranges over these intervals y and g. Right? So now you think about these intervals y and g as being the elements. And we're doing LIS over these elements, over these intervals. Sorry, the intervals are the elements. Yeah, there are bigger elements, right? This is, we are doing LIS. I mean, it's a, formally speaking, a generalization of LIS problem where we don't have characters which have total order, but we have intervals which do not have total order. It does create some problems. But turns out that we can map these intervals back to integers to reduce back to the LIS over integers, which is another approximation. But it's possible. Okay. Now this is a problem where we are basically taking the LIS over these intervals, okay, and a particular interval character in the LIS contributes to the LIS if it is genuine, right? Whether the LIS recursively in that block restricted to the corresponding values is sufficiently long. Very sufficient. So now the new goal is these quantities are obviously the assumption recursive to compute something. Now our new goal for the global LIS problem, so when we are maximizing over these gammas, is we need to solve the Genuine-LIS problem, this one, dotted rectangle. Okay, we need to solve the Genuine-LIS over these Yij elements. But these are intervals for the game. Forget about the elements, the fact that they're intervals for now. Okay, where these genuine flags are defined as follows, right? And this is, testing whether a particular element, where Yij is contributes or not, is expensive, right? So this is why we said that our cost is testing whether something is genuine or not. Okay, so the testing this genuine flag is basically a recursive LIS okay, so basically, the thing that remains at this moment is to solve this genuine LIS problem. All right, so will basically be two algorithms. They start from the same point. So first of all, we identify genuine LIS problem. We're back to solving that one. Is that we have a sequence of characters, and we need to find the length of the longest sequence modulo that some elements are. So what we do is, remember, access to the string is free, right? So we can look over the string and imagine what could be LIS. It's for free. It doesn't pay anything. Okay, so with this regarding genuineness, we do the following. We basically extract what should be the potential LIS elements, right? So this is extracting a set P that for sure contains large fraction of the genuine LIS. Okay? And we do it as follows. Right? So as long as our sequence has an LIS, again, disregarding changes, of length which is about n/k, this is this is our assumption that some LIS of length about n/k. So as long as it is, right, we take those elements, we remove it from the sequence, and we continue doing that until there is no more long enough LIS. That will be, this will be a set P union of these elements. The set P is guaranteed to have, a large fraction of the genuine LIS as well as P. Okay? The only issue is that each particular LIS that we extract in this, the first bullet point, is not guaranteed to be genuine. It could be that, it contains a little bit of our real LIS, but many elements are not genuine. It's just combination from these different LISs will give us the real genuine. Okay. So again, it contains most of the genuine LIS, and there are basically two algorithms. Okay, corresponding to the depth as far as speed, depending on the rate of the genuineness of it for P in particular. Okay, so here's how it works. This is think about this is a direct problem. There's no more recursion. What we do is the following. Again, we're looking for a LIS of length about. Okay, so P is basically our real thing. We sample K elements from this. We test the sample set for genuineness. Okay, and we define P to be the fraction of the set P of elements for genuine. Our estimate, that this is an LIS estimate in the density, will be that it is about P and the. Why is it P? Because why is this the best estimate for LIS? Well, because it could be that each of these this step, when we extract LIS of length n by k, it could be that P is average fraction of genuineness inside the set. So this means that it could be that each of these extracted LIS could have about only P fraction of genuine elements, so that we only have guarantee that about P and by k are genuine. We cannot guarantee any more. And this is I don't know, very simple, but somehow curious idea is to me. But I mean, here is an improvement from the name of. So, well, but we take each of these, extracted LIS, test each of them, what is the fraction of genuine elements, and we take the maximum over all of them, and that should be our estimate. So what this algorithm does is basically takes all the candidates on this LIS subsequences, puts them together, and tests all together for what is the fraction of genuineness. Okay? So instead of using k samples for each of these extracted LISs, we use the same k samples to test all of them for a fraction. And if the average of them has a fraction p, this means that one of them must have p fraction of genuineness. Okay, so somehow it is some form of kind of group testing where to test kind of the fraction of kind of goodness, right, in a bunch of sets, right, we just put them all together, test all together for what is the fraction of goodness. This means that for each particular LIS that we extract here, the number of samples that hit that particular LIS would be a constant. So it is not enough to really estimate. But somehow putting them together, testing all together, guarantees that one of them will have a p fraction of genuine.
So in this way, you put this set together.
There is nothing weighted here. There's nothing weighted, right? I mean, you think about like we always extract, let's say, LIS of size level. And this gives basically 1 over t approximation, right? Because why? Because it could be that the fraction between these extracted LIS, it could be that some of them have much higher rate of genuineness, maybe constant, and some of them have much lower, so average is low. But one of them actually has a genuine LIS of like n by k, whereas what the output is only t n. So this means that we get an approximation of 1 over p, and this is good as long as this p is relatively small of the fraction, which means that the fraction of genuine elements in our sequence is relatively large. Okay, so this is hence the name of dense estimator. It's something that works when the genuine elements are relatively dense. Okay, so the second algorithm is the sparse estimator, and the sparse estimator basically says we just do the sublinear LIS algorithm. So that would be a recursive call on the sublinear LIS. Okay, so just sample, just run the sublinear algorithm, whenever the simplification corresponds to a test of genuineness, something is not genuine, so it is bottom layer of the okay. And why this works, right? Why should this be kind of good whenever this is bad? Because remember, the sparse estimator should be good when the fraction of genuine elements with their sequence is low, when p is very low. But what does it mean, right? This means that we really are improving the p parameter. Okay, so there is some progress, and that improvement is in the following. But if the number of genuine elements is very low, and we're still looking for a LIS of length by p, then among the genuine elements, Genuine-LIS becomes a much higher fraction, which means that we are solving, when we recurse, we're solving a much easier problem where instead of finding an LIS of fraction 1 over k, fractionally the LIS is much higher. This becomes a simple problem. Okay, so in particular, the LIS is higher fraction among the genuine elements. It is n by p out of this p by n. So this means that our key parameter is LIS is of length n by p improves by this factor 1 over p, and the smaller p is, the better the bigger progress. And then over there, you basically take the maximum between these two estimators. You do a very careful analysis of the parameters. Okay, so this is the high-level description of the algorithm. How it does? There is basically one. We will go back and high level and see. Okay. All right. So step back. Let's look at the overall recursion. So the overall recursion is roughly as follows. This is tree of the recursion. That's why there is more nodes here. But think about this as a node corresponding to the entire sequence. This node corresponds to the subsequence x1, corresponds to the block x1, block x3, and the list will be the individual characters of the input sequence 1, for example. Okay, so if you kind of look at this, right, and you kind of put everything together and think what happens, kind of at the end of the day, the algorithm does a form of one of the most recursions. What does this mean? Well, remember, for each block x1 and so on, right? At some moment we'll be doing these genuine tests, which basically are about, given a particular range of values from here to here, compute the longest increasing sequence in this block with values between these factors. Right? So this is an LIS problem. Right? This will be a recursion. This will be a recursion. Okay, but also the top part, right, is this global LIS problem. This global LIS problem, so this is a genuine, we reduce it to the genuine LIS problem. But genuine LIS problem has two outputs, one direct, and one is another recursion over LIS. Right? So this means that once we do this recursion, we recurse in this top portion as well. Right? So it is not just recursing in the box, but also kind of the global picture. And this problem itself will, again, will decompose this into kind of, cut it somewhere in the middle. We'll have local LISs, genuine LIS, and recursing each of them. So this is, this is the high level. But if, there are many parameters to keep track, right? We didn't really kind of go for that. But there is one complex issue. So once you kind of start putting everything back and start thinking about what's happening, there is basically one issue. Namely, that each of the local LIS problems, because we took these candidate intervals, the candidate intervals generated, so for each block, we generated k candidate intervals, which basically corresponded to different potential values, wide values. Let's call my LIS from here to here, or from here to here. And the issue is that this will, basically add some factors k in sample complexity in the runtime. So this is bad, right? So just as is, we do not get plain sample complexity of them. Right? But if you kind of think through that and say, well, of course each of these local LIS actually generated k such problems, but these problems are not completely independent of each other. Many of them are, they're all on this block, and it's not very efficient to kind of take and sample positions and do kind of rejection samples. Well, we sample a bunch of things, and if it's not in this interval, we just throw those elements out. So somehow we need to be more careful about this. Okay, And indeed, it is possible to do that, right? And this is this is a separate idea from the paper, but I wanted to highlight is that the way the sampling is done is a little bit different, and the sampling we will do all the sampling at the beginning. It is non-adaptive, okay, and it is processed in a data structure, but will allow us to reuse the same samples. And in particular, remove that problem of rejection sampling inefficient. Okay, when shall I finish? What is the how much time do I have? Okay. Hopefully 5 minutes. So kind of thinking through the problem and seeing kind of at what rate we need to sample. Basically, we need to be able to remember that this is a recursion. This is a sublinear time algorithm which will sample some of the blocks at some moment, right? Each of these one is also a sublinear time algorithm that will also sample some of these corresponding leaves. Okay, and what we need is to be able to do for any parameter kg is to for a random sample of kg leaves from here, not random, but it's a random uniformly random. We need to be able, but from corresponding leaves, we need to generate k divided by kg leaves. The total number of leaves that is sampled here is about k. Okay. One thing that is clear, but this is definitely not a uniform sample. So uniformly sampling positions from the subsequence is definitely not like this. Okay. And the idea here is, to use something called precision sampling and kind of a generalization to what we call precision tree data structure, which basically samples the tree in a particular way. It's not uniform. There is a notion of precision for each node, and it is defined recursively. So the precision for a child is basically defined by some random number from 1 to beta, so for beta is being subpolynomial, and you treat the nodes where the precision gets to be too high. So think about that. You start with precision 1 over the root. And you sample this according to this kind of random process. The nodes which get precision which is higher than 1, we just stream off and we just don't subset there. Those. And it's there is kind of a statement that says that this precision tree sampling is useful, it can be applied for certain class of sublinear algorithms where you have a sublinear algorithm kind of on this G function, right, which is kind of the global function, right, like the top part, right, combined with the sublinear algorithms for these F functions, right, which are kind of the local functions. I know this is like a very high-level discussion, so pictures, really. Once we sample this in this particular way, on top of it, we build basically 2 range recording data structures so that we quickly generate the right samples in any given block for any range of them. Well, let's see. For now, except that this precision sampling, I'm working on this when I was a postdoc at Princeton more than a decade ago. But yes, so precision sampling is something that was created here. Okay, so this is all I would say. It's not much later at 1:15. So let me conclude, and I want to just highlight the open comments. Okay, so as a statement, what we've shown is that we can estimate the LIS non-adaptively, so non-adaptive samples up to subpolynomial factor approximation in runtime, which is the optimal. Extra factor in runtime is also subpolynomial. The most natural question is, can we get better approximation? Our approximation is, just barely subpolynomial, and comes out as some optimal value for some nasty looking recursive formula. We have recursion both on the global field and on the local ones. We believe that the main barrier is probably getting faster algorithm for this Genuine-LIS model. This trade-off between dense and sparse, more interesting algorithms than that. Again, it's like one of them is just recursive on some linear-LIS, the other one is pretty straightforward with a bunch of things, tests for genuineness. The cool part is that to motivate this problem, we can improving the approximation for LIS, this near optimal time, directly implies a new linear time algorithm, actually linear time for longest common subsequence with the same approximation for the equals. Okay, so you get polylog approximation for LIS in this near optimal runtime. You get polylog approximation for L6, and that would be amazing. Okay. And kind of high-level perspective is that as far as I can see, we don't see concrete barriers. There are no barriers, but we don't have any concrete barrier even to, let's say, getting to one conception approximation for LCS. And let me here compare or contrast with the related problem, basically of that of computing eddy distance. So it's eddy distance, you can think about this as basically n minus longest common subsequence. So the complement of LCS. Of course, approximations from one doesn't answer to the other. So for eddy distance, there has been kind of more progress recently, but people can compute the distance and up to constant approximation in near linear time. But there, for example, there is a much more concrete barrier. There will not be the barrier, but basically all the algorithms there will hit this approximation-free barrier because they use triangle inequality, and the best use of triangle inequality will give approximation factor free. Okay, so it feels like there, something very, very different, remarkably different has to be done to get around this free. Okay? We don't see a similar kind of barrier for LCS. There is not enough. Okay, or on the opposite side, right? If you believe that there should be lower bounds, right, and say, well, maybe we can prove that longest common subsequence is very hard to approximate, let's say even to polylog approximation under Ceph, for example, right, under strong spatial length hypothesis. Well, if you believe that, right, then you should at least prove that you cannot do this for LIS. Right? For LIS at least, because of this kind of black box reduction, LIS is a sublinear time algorithm, so there we can prove unconditional lower bounds, right? Because it's a sampling algorithm, so one should be able to prove, at least technically we have the techniques to do that, right? To prove lower bounds for sublinear time algorithm. Okay, so motivation for understanding what is better approximation. Some other problems are at the moment what we get is estimating the length of the LIS, which means that it gives us length for the longest common subsequence, but not the actual longest common subsequence. So the to find the actual longest common subsequence in a time, probably is a little bit more accessible. And the other kind of connection is just to relate to this my favorite open questions is here is a open problem which is open for about 2 decades now, is to find streaming algorithm for longest increasing sequence in the streaming model with space which is less than. So you have a sequence, you have streaming access to it, and you want to estimate the length up to some approximation. It is known that you can get root and space and approximate it up to one sectional approximation. Our algorithm gets much worse approximation, obviously, but still some polynomial, still about the same space, and it does simply by sampling. So it would be interesting to see if we can using the new ideas for LIS to somehow improve the streaming algorithm. Okay, this is all I have for now. Thank you.
It seems that it does some.
Well, I mean, in root and about root and samples, so LIS is of length root n. Right? So if you do root and samples, this means that you hit about only, let's say, constant or polynomial number of these elements from the true LIS. So you want that, right? I mean, that's in a sense the point, right? That the runtime is optimal up to n to the power of 1, which means that the number of elements from your LIS will be n to the power of 1. So very far from getting all the elements from it. And like one place where you don't see the LIS at all, is this dense estimator for LIS, where you take a lot of LISs and a lot of potential LISs, right? And you say, well, some of them actually have something and some don't, right? Depending on the Genuine-LIS flags. And instead of testing each of them separately, you take them in aggregate and test all of them. And the fraction is high enough, you know that one of each one. But I agree, kind of, out of all these problems, probably this is the most accessible kind of.
What do you get from the reduction PH the exact version outside?
The original will get I mean, it's very sensitive. But it's like the LCS itself is polynomial small, and probably the gap. I mean, there is the factor approximation is probably 1 plus 1 over polynomial. I think there are. If I remember correctly, there is a statement that says for deterministic algorithms, understand you can't beat 1 plus 1 over log n. So not even 1 plus epsilon, even for deterministic algorithms. Right.